here's how limits and continuity all work with composition. So suppose that f is a continuous function at the point where x is equal to L. Then the limit as x approaches c of f of g of x is the same thing as f of the limit as x approaches c of g of x. In other words, the limit symbol and the continuous function symbol are interchangeable. Or if you like, limits go through continuous functions. So the same way limits behave well with sums and differences and products, limits behave well with continuous functions when it comes to compositions. And then what follows immediately from this thing is that if the inside function g of x is also continuous, then the composition f and g must be continuous. And we can see the reason for that right off the bat. Let's take a look at a proof of both of these things. They'll take one line each. All right, here's a quick proof of both of those previous items from the theorem. So if, and we're going to suppose that f is a continuous function. So if we say that the limit as x approaches c of g of x is equal to L, then the limit as x approaches c of f of g of x, well, if I let u equal g of x, so we'll let u equal g of x. Now that says as x approaches c, u will approach L. And so now this limit is the same thing as the limit as u approaches L of f of u. That's that old u substitution rule for limits or compositions. And so now what's the limit as u approaches L of f of u? Well, f is continuous, and so limit is the same thing as value. So I just plug in an L everywhere I see a u. Well, what is f of L? Well, L is just this thing. So I can replace L with that limit, and so now that says that the limit of the continuous function is the continuous function applied to the limit. So that was item 1. Item 2 follows immediately from item 1. If g now is also continuous at x equals c, then the limit of this composition, well, from item 1, I know I can switch f and the limit. So now that's f of the limit as x approaches c of g of x. And now g is continuous. So I know that limit and value are the same. That means I can just plug a c in everywhere I see an x. So that's f of g of c. So now the value of the composition at x equals c is the same thing as the limit of the composition at x equals c. Therefore, the composition must be continuous. Okay, so here's another theorem. All of the elementary functions are continuous everywhere on their domain. And the reason is we know that the basic library functions, those are all continuous. And we know how to get to the elementary functions from the basic library. That's just these algebraic operations, inverse and compositions. So these things are continuous. And then we know that continuity behaves well with respect to these operations. Therefore, anything that we obtain using these operations will give us a continuous function, as long as we start with continuous functions. So any of the elementary functions that you can think of, those things are going to be continuous everywhere on their domain. So here's our first algebraic example. We want to discuss the continuity, or in this case, we just want to find all points at which this function natural log of 2 minus x over x squared minus 9 is continuous. So first thing we want to do is just try to identify this thing as an elementary function. So for example, the numerator is a composition of the natural log function and the linear function 2 minus x. And the denominator is just a polynomial. And so this function is a fraction of a logarithmic function and a polynomial function. So because we obtained this function using a quotient of 2 basic library functions, this thing must be an elementary function. So we know it's continuous everywhere on its domain. So to answer the question, where is this thing continuous, it's the same thing as just finding the domain of this function, just like you did in high school, right? So let's go ahead and do that now. All right, for this example, I'm going to sketch the basic idea of what the answer is, but I need you to refer to the notes, the transcripts of this video to see how you write down a good, complete solution of this example. Most of these problems in discussing the continuity is more about writing good, concise mathematics. So this is much more of a writing exercise that the board is too small for me to write everything down that I need to write down. So please refer to the transcripts of this video for a complete solution. But at least we can say at which points this function f is continuous. So again, the function natural log of 2 minus x over x squared minus 9, we know that's an elementary function, so we know it's continuous everywhere on its domain. So all we have to do is find the domain of this function. So we can split this thing up as a product, if you like, and there are many ways to do this. I'm going to write this thing as natural log of 2 minus x times the function 1 over x squared minus 9. So this is a product, right? It's a logarithm times a rational function. So we know that the logarithm is defined whenever the thing in the parentheses is bigger than 0. So we know this thing is good when 2 minus x is bigger than 0. In other words, if I add x to both sides, that tells me that x must be less than 2. So if I've got my number line here, I know that the domain of this first piece is all of the x's strictly less than 2. So an open circle means strictly less than. What's the domain of this thing now? Well, it's a rational function, so I know the function is good when the denominator is not 0. Well, when is the denominator equal to 0? Whenever x is equal to plus or minus 3. So here, the domain of this second function is all of these x's and remove negative 3 and 3. So now what is the domain of the whole product, or the quotient? So the top function is good here, the bottom function is good here, so the quotient is good at the common part of these two things. So where do these two regions intersect? Well, it looks like I've got an open circle here at 2. There's, we can read in x values all the way up until we get to negative 3. And then after negative 3, we've got more common parts. So here in the shaded region is where this function is continuous. So this thing is continuous from negative infinity to negative 3, union 3 to 2. Or sorry, negative 3 and then to 2. So this would be a good final answer or a good summary of the discussion of where this thing is continuous. Again, please refer to the notes to see how to write this up properly.